hold on. We shall be looking at this chapter 20. Okay. So we shall be looking at this chapter 20 here, the silicon controlled rectifiers, briefly because it is what has been commonly asked a lot, and I want to take you through the ABCs of this silicon controlled rectifier. So briefly, that is what we are going to talk about this evening. Maybe if I get time, I'll go back to the full wave rectifier, but I want to finish the thing of half wave rectifiers once and for all. We'll see how they function, and then we shall talk about also the full wave rectifier. So first and foremost, this silicon controlled rectifier, silicon controlled rectifier. This SCR is a device used for controlling the output, provided there is a given input. You get? So what makes it different from all the other kinds of power devices is that for it is able to do what? To control the output when you have a certain input. This silicon controlled rectifier is a 3-terminal device. It has 3 terminals. That is the gate, the cathode, and the anode. So it has 3 terminals, that is the gate, the cathode, and the anode. And today we shall be looking at how this device functions. What does it do? How is it used for rectification? And what is the output? We shall look at also the calculations and see also other things as we shall come to discuss. So briefly, if you are to look at the SCR, as I told you earlier on, just a moment. Yes, so as you can see, this SCR is a 3-terminal device. As you can see, they get there, the anode and the cathode. First of all, you need to know that it is made up of 2 junctions. It is a PN device made up of 3 junctions. That is to say, the PN. So as you can see, it is a PNPN device, and it is made up of the following junctions. You can see that the anode is the positive end, the negative end is what we call the cathode K, and the gate is connected right around there next to the cathode. So that is just briefly about its structure. And then we also have to look at its schematic diagram. For example, the schematic diagram of such a device is, as you can see, it is always represented with a diode symbol, but having some sort of input here called the gate, this being the cathode and this being the anode. So just a moment. So if you can see the area displayed around your screen is displaying this device, how it is being used as a its terminations. Sorry, just a moment. nzije ku video kiri kuntawa gundi lupapula luli kuntawange teruli kutuuka bulungi. Obani ali kubuuza, are you talking? Your mic is off. Mugambe we are coming. There are 6 people already.
No, we have paused for a while, but we are coming back. A minute, please.
So sorry about that. Briefly, I was just handling something little, but I was talking about this device here called the anode. As you can see here, the SCR. As you can see here in this diagram here, I was just trying to draw briefly what an SCR looks like and its circuit symbol. So I'm not going to bore you with the theory of this thing and how it works, but I'm going to take you briefly to its functions, what it is used for, and then we shall also look at how it is used for rectification and its other applications. Am I audible enough? I hope I'm audible enough. So as I said, I was not going to take you through the theoretical part of this thing, but I would rather opt to take you through the practical bit of it, which is to do with the calculations and to do with its applications. Yes, in case you have a comment to say, please just unmute your microphone and say something, because I will not be able to keep switching here and there to see when you've raised up your hand. But in case you have a question, just unmute and then you speak. So let us go ahead and look at this SC, this SCR. So the SCR has a several number of applications, and we have said that the SCR is used for controlling. It can be used for rectification, okay? And the kind of rectification used is what we call controlled rectification. So when they say controlled rectification, is just simply changing AC to DC, but while controlling the power that is being output to any device that is connected to that circuit. So how does this thing work? First of all, an SCR has several modes of operation. This SCR, as you can see, in case of mode of, if I'm to explain the mode of operation, this SCR is connected in a circuit with always a load in series with the anode, and then it is given a certain voltage across the load. For example, if I have my SCR like this, and it is being connected to a certain load, and this is the certain voltage that we want to control that is going to appear across the load. And here we shall have what we call the gate. You always need to know that for an SCR to be connected in the circuit, it has to be connected, the load has to be connected in series with the anode. This is the anode, this is the cathode, and this is the gate. So every time they are connecting such a device in a circuit, they connect the load in series with the anode, positive, negative, and they always make sure that the anode is positive with respect to the anode. So this device can be operated in two ways. That is case one, when we have an open gate. So this what I've drawn here is the circuit whereby we are having an open gate, and this voltage appearing across the anode and the cathode is what we call the supply voltage Vs, or the applied voltage Vs, and this load resistance is, this RL is our load resistance, RL. So when the gate is open and we apply a certain supply voltage, okay, there is something that is going to happen. This thing here won't be turned on because the gate is open initially. So initially, with the gate being open and we apply a certain voltage across the anode and cathode, this voltage here, the SCR will not be able to conduct until the voltage, the applied voltage Vs reaches a certain value. Until the applied voltage reaches a certain value, which is greater than a certain limit voltage. So when you look at this page of the paper where they are talking about the working condition, they're saying in a silicon controlled rectifier, the load is connected in series with the anode, which is what I have shown you. So which is what I had earlier on communicated. So the working of an SCR can be studied under the following two heads. That is when the gate is open. And when the gate is open, the circuit with an open gate, no voltage applied to the gate. Under this condition, the junction J theory, now we are talking about the junctions. But previously, if I'm to take you back to the junctions here, as you can see, as I had labeled earlier on, these are my junctions. There is a junction J1, this is J2, and this is a junction J3. So this SCR will vary according to these PN junctions. So maybe allow me to draw a circuit so that I can explain the mode of operation when this circuit is like this. For example, if I'm to redraw this circuit here, and I redraw it using this kind of naming, the PNP naming, I'll have that my SCR will look like this, with a P, N, P, N, and then this is the load resistance RL, and here is the supply voltage V supply. So this is the supply voltage, this is where the gate is connected. So when we connect this thing in such a circuit like this, these are my junctions J1, this is my junction J2, and this is my junction J3. So what will happen when we connect and we don't have any applied voltage? So first of all, in this kind of a scenario, we shall observe that this point, junction J1, for example, if this point is connected to the positive, that will mean J1 is forward biased, okay, biased. If we connect this side also to the negative, that means this junction J3 is also what? Forward biased. But that leaves us with junction J2, which is always the opposite of what is happening. So junction J2 will always be reverse biased. And due to this reason, the SCR will not conduct. Okay, the things are stated in the notes around there. So during this condition, the SCR will not conduct. But then what happens afterwards? So the SCR will not conduct. But if you keep on applying this voltage across that junction, across these junctions here, something will happen to these two junctions. For example, if I keep increasing this voltage here, a point will be reached when this junction J2 will break down. And when it breaks down, this SCR will start conducting the anode current. The anode current is simply this current here flowing through the anode, as you can see here. This current here flowing here, I can call it IA, is what we call the anode current. So this anode current here will start to increase, and when that anode current increases, the SCR will start conducting heavily. Okay, so the voltage at which this thing occurs is what we call the voltage at which this occurs is what we call the breakover voltage, as you can see here. When the SCR is turned on with the gate being open, that voltage at which that happens is what we call the breakover voltage. Then other things are so theoretical, I just want to rush through, then I look at the calculation bit, because this is theory, it can be explained. So here they are saying when the gate is positive with respect to the cathode, the SCR can be also made to conduct. What will happen is that these junctions here, so what will happen is with these junctions here, so with the junctions here, for example, if I'm to redraw my circuit, what do they mean by making the junction J3 positive with respect to the other? So we are going to draw a circuit, and we shall have these devices like this. For example, I have my P, N, P, N. Okay. So I have my P, N, P, N like this. And then, sorry about that. So I was saying, for example, if I'm to redraw my circuit like this, and I have a P, N, P, N like this, and then I have the load resistance RL through here, and then I have the voltage being applied across the resistance. Then this side I have my gate. So my gate is going to be powered now. It will have a certain voltage across it, such that there is a certain current flowing through that base. So what will happen here is that in the P type we have holes, and in the N type we have electrons. So when this port here is connected, as you can see in this other diagram here, so what is happening is that, if you can see this clearly, when this part is connected like this, what will happen is that this gate here will receive some positive charge and the cathode will be negative. So by conversion, electrons will move from the negative and become here, they will accumulate at this N type, while protons will come and accumulate around this point here, which is to make it more positive. So instead of using protons, they use holes in this kind of explanation. So what will happen that electrons and protons will electrons will cross over this junction J2, J3, and also holes will try to cross over this junction J3, constituting by, in turn, they will constitute a certain gate current Ig to start flowing. So when there is gate current which is flowing, also an anode current, a small anode current will flow. And as you can see in this section here, as the anode current flows, all these things are explained in that theoretic part of it. So, but as this anode current tries to flow, the n-type will become more negative because of increased electrons flowing this side. So electrons will move from here to try to enter here, and now that will cause accumulation of electrons at a certain junction J3. So this accumulation of electrons will lead to it will cause junction J2 to break down, and when it breaks down, the AC arrow will start to conduct heavily. So what am I trying to mean? Let me try to explain it from this side. So when you can see the circuit like that, the way they have drawn it, maybe if I'm to re-energize this part of it, this is the p-type. Now here we have an n-type. Now here the p-type, the p at this point is where the gate is being connected. I'll draw there holes. And this side is where we have the n-type, where we have electrons. Okay, so this n-type is connected to the certain gate value like that, and also this p-type is connected to a certain voltage, as we had explained earlier on. So what I was saying last time is that when this thing is connected like that, a certain gate current Ig will start to flow. The reason being that electrons will try to jump over this junction here to cross over and go to the other side. So in turn, this movement of electrons, remember, whenever there is a movement of electrons, there is what we call current. So when there is movement of electrons, a certain gate current Ig will start to flow. Now whenever you reach the gate current flowing, also the anode current, maybe Ia, will start to flow. And when the anode current starts to flow, remember, electrons move from this side. So the electrons will come here and try to make themselves available at this point. So when electrons increase, there will be an increase in anode current, and then junction J3, sorry, this was J2, this is J3, and this is J1. So junction J2 will break down because of this accumulation of electrons, and when it breaks down, the SCR will start to conduct heavily. So you can say that the SCR starts conducting heavily. And when the SCR starts conducting heavily, that means the gate, these are just the marking points, the gate loses control. So when the gate loses control, now the anode current can no longer be the anode current can no longer be done what? It can no longer be controlled by the gate current, but rather now there are other mechanisms of which it can be switched off. So the theory there is also examinable, but I'm going to skip forward and try to look at other things, which is the practical part of it. So just taking you through this point here they are just simply talking about the mode of operation of this device, as you can see. Then there are also some other major points. For example, here the conclusion part, they're saying the following conclusions are drawn. An SCR has only two states, so these are essential. An SCR has only two states. That is, it is either off or on. That means it is either does not conduct or it is conducting heavily. And there are also two ways of turning it on. That is, the first method is to keep the gate open and make the supply voltage equal to the breakover voltage. I will explain that slowly in the next section. Or you can apply a small positive voltage to the gate, and that is what qualifies to be the normal way of switching an SCR on. Then also, to open the SCR, i.e. to make it non-conducting, we have to reduce the supply voltage to 0. So with that, allow me to first ask you, do you have any questions before I proceed? Because from here I'm going to run away to straight to the calculations. The other theoretical part is really readable and it is understandable, but I want you to get the calculations bit of it, so that you can know how to calculate for the because here in these calculations we always talk about efficiency, power, and also certain things like ripple factor and others. So if you have any question, please unmute at this moment before I proceed to the next part of this session. So the silence, I hope the silence means we are still together. Anyway, so to continue with this, there are certain important terms. It is so there are some important terms in this section. For example, what I was talking about is there is what we call breakover voltage. Now, breakover voltage is simply that voltage is the minimum forward voltage gate being open at which the SCR starts conducting. Then peak reverse voltage, that one we know it. Then holding current, also that one I'm going to explain also, and forward current also I'm going to explain. So before we go to that,
Excuse me, which chapter is this that we can all follow?
yes, this is chapter CH20, the one about the silicon controlled rectifier. So to continue with this brief overview of what we are looking at today, briefly, what I was considering to talk about is this SCR. And the SCR, after talking about it, we know that it is a two-port. It is a three-terminal device consisting of 3 junctions, PN junctions. So it is made up of such a structure that it is PN, P, and this is just a summary of what I've been talking about. It has 3 terminals, that is the gate, the anode, and the cathode.
Excuse me, pardon, you said it is a 3-port device?
It is a 3-terminal device. It is a 3-terminal device. So I was saying it has 3 terminals, and the terminals are the gate, the anode, and the cathode. So we need to know also its symbol, that its symbol is such that it is like a diode, but with a certain input here, which is what we call a gate. This is being the cathode and the anode. So under normal operation, the anode is kept positive relative to the anode. So the anode is negative and the cathode is kept positive. Now the gate terminal here is what is used for controlling the output, because it is a silicon controlled rectifier. So to control the output, we need to control it by using the gate. Are you saying something?
No.
Okay. So to continue, we say that this SCR has two modes. The SCR is either on or off. By off, that means it is not conducting, and when it is on, we know that when it is on, it has to be conducting heavily. Okay, so those are the two modes of operation. It is either on or off, and it is either conducting heavily or not conducting. So we say it can be, its mode of operation can be looked at in two cases. The first case is when gate is open. When the gate is open. And when the gate is open, we say that at this point here, we shall always look at the gate being open, it and varying the supply voltage, this V supply Vs, and varying it. So whenever the gate is open, we have to vary the certain supply voltage such that it reaches a certain voltage. So when the gate is open and the supply voltage is small, the SCR won't conduct. But by varying this supply voltage, a state is reached when a certain junction which we have looked at, which is J2, breaks down and the SCR starts conducting heavily. And we say the voltage at which this occurs is what we call the breakover voltage.
Excuse me.
Yes. Sorry? Madam Caroline, you were saying something. Okay. Makawesi mulalu. Kawesi. Ese mujiwumuze konse.
Comió.
Simu jiwumuze kyekanye nagikozesa fugo. Oba obadde ogenze paka wa?
You want to be me? Yeah, what should I?
So, sorry, I lost you there, and something small happened. You were asking a question. I left you asking certain question. I didn't get the question. Please
I was requesting that we make a brief statement out of those words you're saying when the gate is open.
a brief statement about the gate being open.
Yes, what we can write here when the gate is open.
So I was saying when the gate is open. Now that is a whole explanation, but I was trying to break it down. So when the gate is open, maybe let me try to summarize it here for you. So what happens when, case one, when the gate is open? So when the gate is open and the SCR is positive with respect to the anode. So when the gate is open, and the SCR is positive relative to the anode, what happens is that, sorry, just a moment. Just a moment. So I was saying when the gate is when the gate is open and the SCR is made and the anode is made positive, this is what is happening. So we have the terminal like this. Now we have to talk about the junctions. This is the supply voltage, Vs. So in brief, what is happening is that the SCR will not conduct, meaning there will be no anode current but when the supply voltage is varied, a certain state is reached when a certain junction J2 breaks it down and the SCR starts conducting. Okay, so we are saying when Vs is varied, a certain state is reached when J2 breaks down and the SCR starts conducting. Now at this point, this voltage that I've described here, the voltage that I've described in this state, is what we call the breakover voltage. So when they ask you to define breakover voltage, so the voltage at which this whole scenario occurs is what we call the breakover voltage. So when they ask you to define breakover voltage, you can simply say breakover voltage is the minimum voltage with the gate open at which the SCR starts conducting heavily. So to summarize it for you, you can say that breakover voltage is the minimum voltage comma, gate being open, at which the SCR starts conducting heavily. So breakover voltage is that minimum voltage, gate being open, at which the SCR starts conducting heavily. Are we together?
Yes.
So that is simply that first state whereby we have the gate being open. Next, I'm going to look at what happens when the gate is mode positive relative to the anode, which is what I was trying to explain earlier on, which is my second case. I'll say, let me call it case 2. So I will call it case 2, and this case 2 is when gate is positive with respect to cathode. So now this one is the wordy part of it, because it has a lot of words to talk about you have to talk about the junctions and what is happening, but I'm going to try to summarize it. So when I was explaining it earlier on, I had briefly drawn the circuit diagram and explained what is going to happen at that point. So the circuit diagram, I'm going to share it with you briefly. Let me get it where I've drawn it. Yeah. So the circuit diagram, let me try to just redraw another one. So the circuit diagram is something like this, whereby we have Pn, this was positive and this was negative. And we say that at this point, if we are told we are going to connect it in such a way that the gate is positive, we shall have a certain gate voltage over here, and we shall have a certain bias voltage. Remember is to draw here a certain resistor, something like that. So what is happening is you're going to first of all talk about the gate current, because this is my gate, this is my cathode, this is my anode. So you're going to talk about the gate voltage, you will talk about the gate current, and afterwards you mention something to do with it, the electrons and the holes in these two sides. So I said that when the gate is made positive with respect to the anode, electrons will, remember this is my junction, J3, this was J2, and this is J1. So you talk and mention something that when the gate is made positive with respect to the anode, with the to the cathode, electrons will cross over junction J3 to fill the leftover holes in the p-type material. Okay, so the movement of electrons will cause a certain gate current Ig to flow. When the gate current starts to flow, immediately you say that also the collector current Ia starts to flow, thereby resulting into, remember when the anode current also starts to flow, now electrons will move from here and come to this point. So that will result into accumulation of electrons at junction J3. So what happens when the electrons accumulate at that point? We say that junction J2 will break down, and when that occurs, the SCR starts conducting heavily. I'm going to summarize them on a paper for you. So, but the SCR starts conducting heavily, and when it starts conducting heavily, the gate loses control. So simply what I'm trying to say is that when the gate is positive with respect to the anode, according to the diagram I've spoken, just to outline the points, is that when the gate is made positive relative to the anode, that electrons uh, will cross junction J3 to fill the, yes, is someone saying, to lift the left, you can call them leftover holes or the left whereas holes in the p-type, So when this occurs, when they try to cross over to fill the left of to fill the left whereas holes in the p-type, something will happen, and that will lead to the flow of the gate current. So gate current starts to flow. And as soon as gate current starts to flow, also immediately, the anode current also starts to flow, and after anode current starting to flow, this will leading to accumulation of electrons at J3. So when electrons accumulate at J3, you mentioned something about junction J2 will break down. And after breaking down, the SCR starts to conduct heavily. So if the SCR starts to conduct heavily, it is said to be turned on. You get it? So when the SCR starts conducting heavily, it is said to be turned on. Now at this point, what happens is that the gate loses control, and then if the gate loses control, what happens? It can no longer control the output. Therefore, that means the anode current cannot drop even though you remove the gate current. This simply means that removing of the gate current or the gate voltage will not turn off the SCR. Do you get the point? Sorry?
Yes.
Okay. So that is simply explaining to us how this SCR is working and how it is, how the modes of operation. We say there are two modes of operation. That is, I mean the modes of operation, and we studied them under the two cases, whereby we said that the first case was when the gate is open, and then when the gate is positive relative to the cathode, as you can see there. Case 2, when the gate is positive relative to the cathode. So with that, allow me to look at now other things are also theoretical. They can be read, but maybe to briefly take you through, let me see. I'll take you through these definitions here, which is what we call the breakover voltage. Breakover voltage, I had defined it earlier on, and we said the breakover voltage is the minimum voltage gate being open at which the SCR starts conducting. Then peak reverse voltage is simply the same definition as previously, the way we have been defining. It is simply the maximum. Is someone saying something?
No, you go slowly on the definition so that we can know it.
Hey, you are writing. Okay, let me get back to the definition. So, for example, the breakover voltage, we said is the minimum forward voltage gate being open at which the SCR starts conducting. That one there, I had given it to you. So I was trying to come and define the peak reverse voltage and also talk about the holding current. So for example, the peak reverse voltage, they're saying it is the maximum reverse voltage cathode positive with respect to the anode. Okay, that one is not necessary to write it, but the maximum voltage, the maximum reverse voltage that can be applied to an SCR without conducting in the reverse direction. So simply what this means is that the peak reverse voltage is that voltage which you can apply across the SCR before it starts conducting. You get, but in the reverse direction. So like the way you can relate it to the diode experience, it is also the similar way you can explain it here. So I was talking about the definitions, and I said this SCR, as you can see briefly, it is also looking the same way like a diode. If you can tell from its symbol, the SCR is just a variation of a diode, meaning it also has a certain voltage that you can apply across it. If, for example, this is the supply voltage Vs, these are its terminals, and the gate is this side. So there is also a maximum voltage which you can apply across it, but in the reverse direction before it starts conducting in the reverse direction. Remember, it is going to be used, it's going to be supplied with an AC signal like this, and it is going to be used as a rectifier to change this AC signal back to DC signal. So that is simply why it is going to have a certain voltage. There is a certain voltage limit in the reverse direction that can be applied across it, as we shall see in some simple calculations in a few minutes to come. So with that, I'm going to rush over and look at the single wave AC rectifier, SCR rectifier. Things like holding current, I will talk about them. Maybe you can just read through that part, because they are also asked, they can be asked, but they're not really that big. Maybe to take you through. Now, for example, here, when you look at this, there is what we call the forward current. There is a circuit fusing element and maybe holding current. So explaining some of these things, I'll need to draw them down here. For example, when an SCR is on a circuit like that, there's a current that is flowing through the anode. Okay, and this current flowing through the anode, is the forward current. There is what we call the forward current, and we are saying by matter of definition that this forward current is the current flowing through the SCR when the anode is positive relative to the cathode. In actual sense, when it is forward biased. I don't know if you can get me, but simply like the way we have been explaining for a diode, that the forward current is that current that flows through it in the forward direction. Even for this one, it is the same thing, just that here we won't say that it is forward biased. Well, we shall just simply say when the anode is positive relative to the cathode. For example, I'll say forward current is the current through the SCR when the anode is positive with respect to the cathode. So that is simply that. Then also these things have what we call a forward current rating. So this here is the definition for the forward current rating. So the forward current rating looking at it, as we saw that a diode has it has a certain maximum voltage that it can withstand before it starts conduct. Okay, it has a certain voltage rating that it can withstand in the forward direction. Even this one here has a certain voltage that it can withstand. So they're saying here the forward current rating is the maximum anode current that an SCR is capable of passing without being destroyed. So what does this mean? This simply means that Even though this diode is forward biased, as you have seen here in the diagram, even if this diode is forward biased, there is also a rating, that there is also that maximum current that it can withstand before it gets destroyed. Okay, even if it is forward biased, there is also that limit that I can only withstand such and such a current before I get destroyed. So that is simply what the forward current rating is. Maybe this other thing what I can explain is what we call the circuit fusing rating. I hate this part because it has a lot of definitions. So I hope you can see my screen. Yeah, but what they're calling the circuit fusing rating is just simply a formula. Actually, you can get it from the formula. So they're saying the circuit fusing rating is the product of the square of the forward surge current. I'm going to explain those terms, and the time of duration of the surge. So to briefly put this to explanation is, when we have an SCR connected in a circuit, remember it is used as a switch. That means the voltage across it will change, and also that means also the current across it will change. You get it? But this current and voltage can change abruptly, as we are going to explain in the near future. So when these currents and voltage change abruptly, even that means this I is what we call surge current. So they're saying the fusing rating, let me write something bigger. The rating is just given by I squared T, whereby this I is what we call the surge, current. And then this T, just a moment. And then this T here that we're saying here is the duration at which the surge occurs. I don't know if I have put that in simpler words, but I hope we are together. Are we together? I hope we
Yeah, we are together.
Yes. So this rating is measured in square amps and seconds. Okay. This current rating, I said, is measured in amps squared seconds. So this rating is going to give us what a system can withstand before before this diode with this SCR breaks over and gets destroyed. So I'm going to share with you a certain question here. For example, here, this is just an example, and it's a common one. So here we have an SCR. They're saying, first, before I go to that example, here it is saying the circuit fusing rating indicates the maximum forward surge current capacity of an SCR. For example, an SCR having a circuit fusing rating of that, if this rating is exceeded, the circuit device will be destroyed. So the brief way I always explain this is I explain it by using by explaining it by mentioning someone maybe touching a candle. You see, these devices are so unique in that the longer you express it to too much current, for example, if it is rated 90 square amps a second, okay, meaning it has a certain current I. This is the I squared T rating is equal to 90 square amps. I'm going to forget about the I squared, the I's being squared, and I just look at the current. I'll say maybe this device can handle 90 amps for 1 second. Okay. Then it can maybe handle 180 amps for a half a second. A half a second. You get it? What is this meaning? If you look at maybe someone touching it, like ladies normally do it when they are removing maybe rice from the charcoal stove, you find that she will just hold the thing, carry it, and remove it and put it aside. But the duration at which she's exposed to that heat is short. Now, for you, you might come and think they don't feel pain, but if you touch it and hold it for a long while, you will not be able to withstand. You might get burned. So, what does this mean? Even these devices here, the longer you expose it to too much current, it will break down. Yes, it can withstand 90 amps, but for only 1 second. When it exceeds 1 second, it will burn. It can hold 180 amps, but for only half the time it would hold 90 amps. If you overexpose it for so long, it will burn and get destroyed. So that is what we call the circuit fusing rating, and that is what it does. I think it can be found in the data sheets. Are we together? So for example, here they have shared with us an example, and they're saying an SCR has a breakover voltage of not this, of 400 volts, a trigger current of that. They are trying to get us to explain. No, I'm not going to do that. I'm not going to do that. I'll do it. That one is going to. It's not a very diverse example that will help me explain so much. So I'm going to rush over and we talk about this SCR as a half wave rectifier. Is that okay? But this example here, I'm not going to talk about it just simply because it is just implementing of those formulas. Because here they are trying to tell you to explain about the breakover voltage. What does it mean? Then they're also telling us to explain about the trigger current, the holding current. It's just explanation of the other formulas that we had stated. So I'll rush to this. This was the example I was looking for before I go anywhere. So I was looking at this example here, example 20.2. They're saying an SCR. I hope you can see. So they're saying an SCR is having an SCR is subjected to a 50 amp surge that lasts 12 milliseconds. Determine whether or not this surge will destroy the device given the circuit fusing rating is 90 square amps. So for that particular example, they're giving us the fusing rating. They're giving us for example, this what you see as 90 square amps is our circuit fusing rating. And this ampere here is the I that we have. And this time T is the T we have. They want us to find out if this is going to be destroyed. So what they're doing here is simply putting it in the formula. Let me write down the equations. So they are saying that this device is having a certain fusing rating. They are saying the SCR in a circuit having a surge current. So the surge current, our I, is equals to 50 amps. And they're saying it is subjected to a surge that lasts for time equals to 12 milliseconds. They want us to determine whether or not this will be destroyed given that our I squared T rating is equals to 90 amps squared per second. So what we are going to do is we are going to simply calculate First of all, we calculate what would be the surge rating for such a combination of inputs, and then we shall compare it to this and see. This will be destroyed if what we get here is greater than what is given. But the SCR will not be destroyed if what we get after calculating these two is less than what we have there. For example, we shall say I squared t is going to be equals to our current, which is 50 squared, times our time, which is 12 exponent negative what? Negative 3. So putting in this into the calculator is going to give us a 30 amps squared second. And this value here is small compared to that value there. So after this comparison, you can simply say that since the circuit fusing rating of the given values is less than the total rating of the circuit, therefore the SCR will not be destroyed. Is that okay? Any questions?
Come again with the conclusion. Please repeat the conclusion, sister.
I was saying that for the conclusion, I was saying that since the value that we have got after calculating is less than the given circuit rating, therefore we say that the device will not be destroyed. What I'm saying is that since the value which I mean is this value here is less than the it's called current fusing rating, therefore the SCR will not be destroyed. So that is just the brief explanation about that. So any other question? Because what I wanted to briefly introduce today is so different, but I see time is rushing and people are kind of exhausted. But I hope we are together there. Are you people still good? Can I give you something small before? Something about the half wave and half wave rectifier of the SCR. Oh,
Yeah, we can push on.
okay. So I'm going to proceed with this SCR circuits here. And I was trying to say that an SCR, we said it can be used for rectification. So we are going to look at the silicon controlled rectifier itself. SCR rectifier. And we say that this SCR can be used for rectification, and it can be used in two modes. The first mode being the half-wave rectifier, and the second mode being the full wave rectifier. So it is simple like the diode. The circuit forms are the same, but just that This one here is a controlled output. The other one isn't a controlled output. So allow me look at the SCR half wave rectifier. So an SCR half wave rectifier is just something similar to what we have been looking at. SCR half wave rectifier. So this SCR, which is being used as an half wave rectifier, it will automatically have an input, an AC input, which I can represent by through a transformer, and then I'll have the secondary of the transformer being connected to a load, and then through an SCR. Remember, we said that the load is always connected in series with the anode. Now this anode here, this point here is going to be controlled, and here we shall have, now I've drawn a very small circuit, but it is controlled through a certain resistor, and then it has a certain voltage across its terminals. Allow me to draw it like that, though it is so small. So this resistor here is a variable resistor R. It is what we use to control the voltage to the gate. And then this is our load resistance RL, and this is our SCR, and this is our primary and secondary. So to explain this is simply the same way we have been explaining, maybe assuming we have end A and this is end B. You explain it the same way we explain a half-wave rectifier of a diode. For example, you can say that during the first half wave, during the first half cycle, remember we're having an AC input as follows. So if this is an AC input, we expect to have a DC output. Let me put here my output. So I'll have an output at this point here. So what is going to happen is that during the first half cycle, when end A is positive relative to end B, and provided that this thing has been triggered, the SCR will conduct at a certain voltage V. And during the negative half cycle, when end B is made negative relative to end A, the SCR will be turned off and will not conduct. But what I wanted to explain is simply at the conduction angle. Because this is a controlled output, there is a reason as to why it is called an SCR. Because now we're going to try to talk at it as if we are discussing about this item here. So this voltage here, the output of an SCR, will not be there. Even if it is positive, it will not be there until this gate current is at a certain value. So by varying this gate current, we vary what we call the firing angle, and this SCR is always turned on at a certain angle called the firing angle, and it will always conduct as long as the voltage has reached what we call the firing angle. So what am I meaning in this case? What I'm meaning is simply that for this SCR to conduct, remember we have a gate current. This gate current has to be at a certain value called the gate triggering current, IGT. So once you set your gate current to a certain value, meaning you're varying the voltage at which this SCR will turn on. Okay. Previously, we saw that when we don't have a gate current, this SCR had to be turned on when the applied voltage was greater or equal to the breakover voltage. But when we apply a certain current, this SCR will be turned on at a much smaller voltage depending on amount of current we have turned on. So this thing here is like, let me say the way you see a volume knob. You increase this resistance, you are controlling the gate current. When you're controlling the gate current, you're determining the voltage at which this thing is to be switched on. Am I together there? Are we together on that point? I'm waiting for your reply. Or do I need to further explain a little bit about that? Mr. Innocent. Tulifena?
So in short, you're trying to mean that, for example, if I vary this resistor here on the gate, yeah, to a very high resistance, yeah, that means the SCR will depend on the voltages that are coming from the transformer, right? Because if I put a very high resistance, it will act as if the gate is open. That's what you're trying to mean.
Yes, exactly. That
Then
is.
if I lower the resistance, that means the gate will conduct, and the SCR will depend on the two voltage sources. That's what you're trying to mean.
Yes, that is exactly what I'm trying to mean. That the when I vary this resistor here, sorry, my diagram has become so foggy. But once I vary that resistor there, I will be varying the voltage at which this device is going to be turned on. So when I vary that, this resistor here, when I'm varying it, I'll vary the voltage at which this device will be turned on. And when it is turned on, by increasing this resistance here, it is like I'm opening the gate. By decreasing this resistance, it is like I'm closing the gate. So that is exactly what I was trying to explain. So for example, if I'm to look at this diagram and compare the output with the input, let's say, remember this voltage here is varying, okay? And now this is supposed to be my output at this point. So let's say I set my resistor such that I've set my resistor such that a certain gate current Ig is flowing. Then this gate current Ig will allow my SCR to be turned on at a certain voltage V trigger, a triggering voltage V trigger. So this thing here in my output, my output will not be on until the voltage all reaches what I call my V getting trigger. My V trigger, my triggering voltage. So meaning that even if it is a positive half cycle, like the way it was previously, this positive half cycle, this positive half cycle will not have any output until for these points here, until the voltage reaches this certain value here. So when the voltage reaches this value here, the output will be there. And when it doesn't, when it drops below this, when it drops below 0, the SCR will be turned off. Again, it will be turned on when this value reaches again this triggering voltage, and then it will be turned on. I don't know if you get me there. So remember that our voltages are defined as V equals to Vm sine theta. Similarly here, this angle at which this is turned on, whereby theta is this angle, varying angle along this path. So this angle at which this SCR is turned on is what I call my firing angle alpha. And this is 0, this is an angle 180 degrees, which is represented as pi. So other derivations are all picked from this particular expression, as we shall see. But it is important to just know that the way this thing is explained, that by varying the resistor, we vary the angle at which the SCR is turned on. Or simply by varying this gate current, we are varying the voltage, the anode voltage at which the SCR is going to be turned on. Thereby we are controlling. So the reason we call it a control rectifier is because it controls that angle. Because we are able to control the angle at which this is fired on. And remember that power of any alternating component is contained only in this duration at which it is on. For example, this particular one for example, it was coming like this. It will be on for this part of the session, meaning it has some power, but it is not having all the power like a device which was on for the entire half of the session. You get it? This one was having power for the entire half of the session. This one is having for only a portion, meaning that the power contained in this is greater than the power contained in this. I don't know if you can see that. So by this is where the SCR has superiority over other devices, other rectifier devices, because for it can control the power in the output of these two devices. I don't know, are we together there? You know, online lectures are weird, I have to agree, because I don't know your expressions, whether you're getting or you are lost. I can't tell the facial expressions, but I hope we are together. Mr. Suman, are we together?
Yes, we are together.
I think we are okay.
Okay, thank you for the feedback. Now, with that, I'm going to go and talk about this wonderful equation. And I think with that equation, many people will be able to do some numbers on SCR circuits. So, briefly, these equations all come from what we have drawn here as our SCR diagram. For example, the main thing that we had drawn is the output waveform of an SCR, and we have said that for its output, it is on for one section and it is off for the other halves of the section, like that. Okay, for example, it is on, then it remains off, and then it goes on, but it goes on at a certain angle which we are defining as our firing angle. For example, it will be turned on at this point, and then it will remain on, and then it will go off again, and then it will be turned on at a certain same point again for the next cycle, and remain on, and then it will go off. So this energy here contained is what gives us what we call the controlled energy. And we said that if this is our firing angle and this is our angle pi, which is also represented as 180 degrees, we know that to get, last time as I was introducing diodes, I talked about what we call mostly the reason as to why we do these calculations is to calculate for the AC power, the DC power, the average values of current and voltage. For example, the I average and this and V average. These average values represent the DC values. Then also we talked about the AC values, which is the first of all maybe Vmax, VRMS, and the I root mean square values. So the main reason as to why we do this is maybe and finally to look at what we call the efficiency of the entire system. So the main reason as to why we do calculations with the AC arrays is to reach the final thing, which is to calculate for the efficiency of the entire system. And here, these are equations here. There's, for example, the derivation that was given in the assignment. These derivations cannot be calculated until you have knowledge of how to find the average values of the current and voltage. So for us to calculate for the efficiency, we know that the efficiency is the ratio of the output to input. So efficiency is the ratio of P out over P in expressed as a percentage, which means multiplied by 100%. But for any rectifier, the output power P out is equals to the DC power delivered to the load, and the input power, which I call my P in, is equals to the input AC power to the entire circuit. So those are some of the things that we have to be putting at heart when we are going to do any calculations involving these silicon controlled rectifiers. Are we together up to there? I've skipped so many things. I've skipped forward to look at this device mostly and how it works, but when we get at this time, when we meet physically, I believe some of you will come and we meet physically. When we meet physically, I will be able to explain, because some things I may not be able to fully explain over this website, or like over the network. But I know with a physical meeting, it is easy to represent these things. So I'm going to look at the AC values of power and the DC values of power of this system, so that we can be, maybe by the end of the night, we shall be able to calculate for the efficiency of any system. So as I was saying previously, I drew this thing here. So to look, if we are to look at the for example, let me start by looking at it. The output power, which is the PDC delivered to the load. Suppose my system is connected to a load of certain load resistance R, L. Suppose my circuit is connected to a certain load of load resistance R, L. As we can see in the previous circuit. Okay, so my circuit is going to be something like this. I'm just redrawing what I previously drew. This is this point, and here I have my load resistance R, L, and here I have my SCR. I'm not going to redraw the triggering circuit, but you continue and finish with the variable resistor and then the other friend of this. So there is a certain current that is going to flow in this circuit, which we call an I. Let me call it I because I'm considering AC values. And there is going to appear a certain voltage across here, which is an alternating voltage. Okay. For example, we know that the output power is the DC power delivered to DC resistor. So this DC value is given by, we know that power is equals to what? I V, or it can also be given by I squared R. Now in this case we are going to use I squared RL because we are always considering the current being the current is always the same, and it is all passing through the load RL, because if we use voltage we shall need to get the voltage across this point, which is very hard. So we shall always need to use I squared RL in order to calculate for anything. But in DC, another important note to make is that for DC, for anything of DC, we use average values. Then for AC here, we use root mean square values. So those are the only two differences that we shall always be looking at while considering these computations. For example, let's say we are looking at the DC power. Now, to look at the DC power, we said for PDC, I said that for DC power, PDC, we are going to consider the average values. So that means I will need to use my PDC is going to be equals to I DC squared times our load resistance. But IDC is equals to I average. I don't know if that is clear. So if IDC is equals to I average, what does that mean? Now to calculate for average value of current, I average is going to be equals to, remember when we used to study in the senior 6 or senior 4, I don't know which class it was, but to get the average value flowing in this was given by the integral of this particular section. It is given as the area of this particular section. And to get the area, we shall say that the area of this particular section we have given maybe okay, from here up to here, because our energy is contained only between here and here. It is always given by 1 out of 2 pi times the integral from where we are starting from. We are starting from alpha and ending at pi. So from alpha to pi of this thing here, which is I, but with respect to theta. But remember that from V equals to I R, okay? That means our I is also going to be equals to V over R, okay? This is just an equation of from this. If the voltage across here is V, and the current flowing here is I, therefore to get the current I will be equals to V over R, just like that. We are assuming that this has no resistance. Are we together there? So my I is going to be equals to V over R. So I will put this inside there, and I'll have my I average being equals to 1 out of 2 pi I lost track of time. You people, it is 11 sharp. I don't know. But let me finish this thing and then we break off, I think. So it will be from integral from pi from alpha to pi of my I, which is V over R with respect to theta. Now initially our V is the the supply voltage, but the supply voltage being supplied here is AC. And we saw that the AC supply, remember this is just the secondary of the transformer. And remember that for any AC value, we know that V is given by a certain value, V max times sine theta. This is just from the expression of any sine wave. Okay, so we substitute this into that equation, and we shall have our I average. We shall have our I average being equals to 1 out of 2 pi integral from alpha to pi of V, but our V is Vm sine theta with respect to theta over R L, which was this R here. Are we together there? So from this point on, we shall just simply pull out what is constant. For example, what does not have theta in it. Remember, we are integrating with respect to theta. So anything that does not have theta in it, we pull it out and remain with what has theta in it. So I'll have my I average being equals to Vm over 2 pi RL integral from alpha to pi of sine theta with respect to theta. Don't know if that section is still visible. Just a moment. So I was saying, so at that point there, we shall have our Vm over this being pulled out, and we shall remain with the integral of sine. And remember that the integral of sine is a cos. So this will be, the integral of sine is a negative cos. So this will be negative cos theta, and we shall put from alpha to theta. Now putting this thing into the equation, we shall have that equals to Vm over 2 pi RL. Now this negative, we can first of all pull it out. Okay, I've pulled out that negative, and I'm remaining with a certain bracket here of cos, but I'll start with cos of pi minus cos of alpha. Is that okay? So at that point, when you simplify, realize that cos pi is what? Cos of 180 is a negative 1. So this is going to give us a negative 1. And at the end of the day, I'll have that this is going to be equals to Vm over 2 pi RL. Now this negative here, I'll remain with a negative 1 minus cos alpha. So from that equation, you can see clearly that if I put this negative inside, this value here will become positive, and this one will also become positive. And that there will give us our final expression of the equation, which says that my Vm, my I average, is going to give us Vm over 2 pi times our RL into, this was 1 plus cos alpha, just like that. And this is the equation that we use to calculate for the DC current that is appearing at the load. So you realize that now, unlike what we had in the previous sessions, here our average value of the voltage is depending on a certain value, alpha, meaning that when this firing angle alpha changes, that means that also our voltage will change. So that is giving us what we call a controlled output. So that is the first derivation that we use in that equation. I'm going to put a star here so that next time I can be able to proceed from this very point of the time. But at this juncture, allow me inviting any few questions so that we can maybe close the night. And hopefully, tomorrow we are having a session of programming still. For those maybe who may not be with us around their coming exams, we have programming, we have their tests, we have programming, we have also power systems and power electronics. They are all going to be in the same week, with programming being on 26th. Power systems is the first on 25th, and then power electronics will be on 28th. Most of the things that we are going to cover are what we expect is to be set, because this gentleman of power systems, has told us that for him he will set Ferranti effect. So we expect that we shall read through this and maybe be able to understand. So our next power systems lecture, we shall be tackling this Ferranti effect, and maybe we shall also look at some other things, because Ferranti is not so big. We shall give it briefly 1.5 hours, and then we shall use the other remaining part of the time to look at other things and revisions. Then tomorrow we shall be tackling Java as per timetable, and then on Java also, this is having an exam. We don't know what she will set. Then we have also power electronics. So far the two topics we have studied, it is okay. Though we haven't yet finished, you are still demanding me something to do with full wave rectifiers, and then calculations. So the next time we are meeting, I'm not going to go through theoretic parts. We shall be only tackling calculations, and then we shall be looking also at the full wave. Also, full wave doesn't have so much theory. We shall basically strictly looking at calculations in all those fields. So this was an introduction to SCRs and also half-wave rectifiers using SCRs. Any questions as we are closing this session? So with that, I think maybe we can close the session and hopefully hope for something better tomorrow. Yes, please say something. Yes.
I 1010 really I appreciate this for organizing such a session. Really, you guys are doing the best. Because really, though I joined late, I thought maybe it was not going to happen because of the days back you guys have been on and off. You tell us we are going to hold a session, then maybe you turn it off. But really, I appreciate your efforts to take us through until this time. Really, I appreciate a lot. I hope everyone gains from this. Really, you're doing the best. Thank you.
You're very welcome. Then also for people who have questions, please, whenever we meet, you can endeavor to meet me. Maybe I can rectify something that I could have explained and you failed to pick online. So please feel free to meet me whenever you see me and you have a question about something we have discussed. I'll give you the service with all the best of effort. I'll be able to explain and expound on such things. Otherwise, thank you. Any other remarks? Okay, with that, I think we should close the meeting and have a good night. Thank you.
you.